Good morning, and thank you for attending to this presentation on the characterization of resident space objects for space situational awareness. Over the past decade, the exponential increase in space traffic and debris has made orbit determination alone insufficient to protect space assets and preserve the space environment. Therefore, we need to extend traditional space surveillance and tracking activities to estimate additional object parameters. For example, attitude, size, shape, or material properties. And this characterization has many applications. For example, the design of active debris removal missions or improved prediction of atmospheric re-entry and collision probabilities. The objective of this work is to estimate object parameters using light curves as the one you see there, in which it shows the temporal evolution of the irradiance recorded by a sensor as the object rotates and moves along its orbit. In particular, we want to estimate the orientation at the reference epoch, the spin velocity, the solar array orientation, which is crucial because it is normally a huge surface, the diffuse reflection coefficients of all the materials, and an atmospheric parameter called aerosol optical depth, which changes a lot with weather conditions. To address this problem, we propose a method based on adaptive importance sampling, in which we estimate the target probability density function by drawing samples from a proposal distribution, which is iteratively refined according to the sample quality metrics. And now I will explain step by step the algorithm. First, we will estimate the average apparent rotation period, applying a Lobes-Carlyle periodogram to the complete normalized light curve. The apparent rotation period is not the real one, it's the one we see in the signal of the light curve. Then we can get an initial estimate of the inertial, the real one, inertial spin velocity. The method is based on the fact that the observed irradiance is proportional to the illuminated projected surface. And this surface is approximately symmetric with respect to the phase under the sector between the sun and the sensor. Taking into account that the light curve pattern repeats approximately each time the object recovers the same orientation with respect to the phase under the sector, we can derive that equation that relates the apparent angular velocity with the inertial angular velocity. And we can estimate the inertial spin velocity parameters, the spin axis, and the module applying a least squares method. The instantaneous apparent angular velocity is obtained with a sliding window applied to the light curve. And the size of the sliding window is determined from the global or average apparent period that we have computed before. Okay, then before starting the iterative part of the algorithm, we need to initialize the proposal distribution of the parameters that are described with particles, the attitude parameters and the solar array. For those for which we have an initial estimate, we use a Gaussian distribution, and for the rest we use a uniform distribution. Then we can propagate the attitude to the epochs of the observations, of the real observation, so that we can estimate the optical parameters and the aerosol optical depth. We need an efficient method because this has to be done for each candidate particle or candidate attitude state. And since we have an analytical formulation relating the diffuse reflection coefficient of each material and the aerosol optical depth with the apparent magnitude, we can estimate these parameters applying a least squares method to each particle. Then we need to reconstruct the observation, the simulated observation with the previously computed parameters in order to get the particle quality metrics. And you can see there the particle weight has a temperature schedule, this exponent, in order to flatten the weight distribution in the early iterations of the method to avoid the risk of convergence to local optima. Then we need a method to update the particles from one iteration to the next. And we do this by a combination of two methods: systematic resampling, which basically replicates particles that have a high weight and eliminates those that have a negligible weight. And it is very useful to prevent the problem of the particle degeneracy. And in combination with systematic resampling, we apply particle swarm optimization that updates the attitude state considering the inertia of the previous iteration, the personal best state found by that particle, and the global best state found by any particle in the swarm. And it is very useful to maintain particle diversity and accelerate the convergence towards the most likely solutions. Finally, we perform a cluster analysis to identify the modes of the posterior probability distribution, so that we can compute the expected mean state and the standard deviation. And this is the convergence criteria that we use to stop the iterative method. So now let me present a test case of an uncontrolled spin-stabilized object. You can see there the satellite model and the reference parameters that are going to be estimated: attitude, solar array, the optical properties of the materials, and the aerosol optical depth. These parameters produce this reference net curve that is the one that we use as input to our method. Here we can see the initial estimation of the inertial spin velocity. In the left plot, we can see the evolution of the apparent instantaneous apparent rotation period. And this instantaneous rotation period is used in this equation to estimate, with a least squares method, the inertial spin velocity parameters, the spin axis, orientation angles, and the model of the inertial spin velocity or the spin period. And here in this plot we can see a parametric analysis on the orientation of the spin orientation angles of the inertial spin axis, and also the least squares estimate that we get. These results are used later to initialize these parameters with a Gaussian distribution. And now we are going to see the iterative part of the algorithm. As I explained before, we start with a Gaussian distribution for those parameters for which we have an initial estimate, and for the rest we use a uniform distribution. Now, by the third iteration, we see that some high probability regions begin to emerge, and as iterations progress, we see how the particles tend to converge to the true solution. In the table, we can see the numerical results of the final estimate. As you can see, we get a weighted root mean square error around 1, which is consistent with the standard deviation of the noise. And these results produce that simulated or estimated light curve. And these are the residuals for each observation. You can see that most of the points fall within the ±2 standard deviation of the noise. The total computation time is around 2 hours, and the most demanding step is the simulation of the observation. So to sum up, we have developed a method that's able to estimate different attitude, physical, and atmospheric parameters, and it is accurate, robust, and designed for computational scalability. And potential lines for future work include the estimation of tumbling objects, also include estimation of the specular contribution to the irradiance. Apply this method to other measurements like the radar cross-section, and improve the computational performance, and apply this method to a real data set. These are the main achievements we have of this year. We have published 2 journal papers and presented 2 conference articles. That's also from my side. Thank you very much for your attention.